elementary, so and abstract. So let me start by recalling the definition. So the G is a group. So the profinite topology on G is the topology generated by all cosets of all finite index subgroups. H in G, right? I recall the notation for a finite index subgroup that I used last time. Okay, so it's always a group topology okay, the open sets are unions of cosets of finite index subgroups. And G with the profinite topology.
So those are the basic open sets.
Yeah, these are the basic open sets.
So the intersection of two.
Yeah,
Okay.
it's the,
Yeah. Okay. Yeah. Go on.
and so this topological group is Hausdorff if and only if the singleton identity is a closed subset, and this is equivalent to saying that G is readily defined. And now, further definition. So given a subgroup H in G, we define the profinite closure of H in G as simply the closure in the profinite topology. And then you can check that this is the same as the intersection of all subgroups J of G which contain H and finite index in G. Okay, so again, there is something to check here. It's an exercise. Okay, and in the special case where H is equal to its profinite closure, we say that H is separable. Okay, and again, so fact, and again it's an exercise, we can, and it's a justification for the term separable. H in G is separable if and only if for every element G of the group G which does not belong to H, you can find a finite quotient of G which separates the element little g from H. Okay, so let's consider a few examples. The most obvious one. So if G is finite, then the profinite topology is discrete. and everything is closed. So all subgroups are closed and open. If you take a free abelian group, then again it's not too difficult to check that all subgroups are closed, are separable. And more generally, if G is polycyclic, then it's a result of Maltsev. That all subgroups are separable. But this is a rather specific situation. So actually, there is a partial converse to this statement. So if G is finitely generating and soluble, then and if all subgroups are separable, then G is virtually polycyclic. That's a result of Susan, James, and John Wilson.
What's the first name there, sorry?
For Wilson?
Susan James.
Thank
Okay, so even among soluble groups, it's pretty rare to have enough finite index subgroups to separate all subgroups. Another classical fact is that if G is free in a free group, then all finitely generated H and G are separable. That's a result due to Marshall Hall in 1949. But, and here the finitely generated is of course absolutely crucial, because in any group, right, if you take a normal subgroup of any group, so what does it mean for n to be separable? Right, it means that n is the intersection of the finite index subgroups of G containing n, and this is exactly the same as saying that G mod n is residually finite. Okay, so and free groups of rank greater than 1, they have non-residually finite quotients, so they have inseparable normal subgroups. Okay, then surface groups, in surface groups, all finitely generated subgroups are separable. I mean, the study of separability of subgroups is a kind of a classical theme. The dimension of topology, I suppose. Okay, so why does this enter my discussion? And the reason is, one of the reasons is from the following lemma. So basic lemma due to long and zero. If G be any group, and alpha an automorphism of G. If G is readily finite, then the centralizer in G of alpha, so this is just the fixed point set of alpha in G, is separable. Okay, so the proof. So alpha it's an algebraic automorphism of G. So it permutes, in particular, the finite index subgroups of G. So it induces an automorphism of the group G viewed as a topological group with a profinite topology. Right? It permutes the basic open set of the topology and it preserves the group structure. So it's really an automorphism of topological groups. Okay? So as we said before, G readily finite. This is the same to saying that this group is Hausdorff. Okay. And now in any Hausdorff topological group, centralizers are closed. That's a very straightforward exercise. And that's the end of the proof. As an exercise, you may want to find another direct proof of this lemma, not using Hausdorff topological group, if you like. You can directly apply the characterization of separability that I'm erasing now.
Actually, it is true also whatever the other topology you define, right?
What did you
If
say?
they cannot finite quotients but some, I don't know, some other quotients, everything will be,
It's not what's
say, residually something, residually p, say,
yeah.
and then you define this p topology. And
Yeah.
then,
Yeah, you can apply this
Yeah.
proof to other topologies than the profinite topology. Yeah. Sure. Okay, and why am I mentioning this? Due to an application that was found by Danny Wise in his thesis. So for any group, let G be a group, and H in G an inseparable subgroup. Okay, then the double of G over H is not readily finite. Okay, and here, so this is the amalgamated free product of two copies of G over H, and I take the same embedding of H in the two copies. Right? And the reason is that, indeed, in this free amalgamated product I define, you have an automorphism swapping the two free factors. And the centralizer of this automorphism is exactly the amalgamated subgroup H. So, and automorphism writing the two free factors, you see the centralizer of alpha is exactly h. Okay. So if this were residually finite, then H would be separable in the bigger group here. It would be closed in the bigger group. But then it's also closed in the smaller group G, because it's an intersection of finite index subgroups of the bigger group, so it's also an intersection of finite index subgroups of the smaller group. Right? So this is a very, very beautiful idea, and so Danny Wise also suggested to use this idea to find non-residually finite hyperbolic groups. So here is what. So another yeah. So this is application 2. Wise. So if G is hyperbolic and H in G is non-normal and quasi-convex, and inseparable. If you find a subgroup that has all of these three properties, then the double is hyperbolic. Okay, this only follows from the first two properties of H. That's by the combination theorem of Lesvina and Twin. And it's not non-residually finite by the inseparability of H. So
The main problem is to find a group subgroup which is not separable.
yeah, absolutely. So and this in itself, I mean, yeah, it's kind of yeah. It was a source of inspiration for many further developments. One of them is it was the condition of normality of H was later removed by Hegel, Groves, and Manning. So let me mention this briefly. So there was a subsequent result with Hegel, Groves, and Manning. Who showed that the following are equivalent. One, all hyperbolic groups are residually finite, and two, in every hyperbolic group, all quasi-convex subgroups are separable. Okay, so in a sense, they managed to promote Danny Wise's argument for more complicated quasi-convex subgroups than the malnormal ones. And this should be, well, this can be interpreted as evidence for the existence of non-residually finite hyperbolic groups, because really, formally, you know, yeah, this says that hyperbolic groups have many finite index subgroups, but the second really tells you that hyperbolic groups have an amazing amount of finite quotients. And you can make this slightly more precise. Perhaps I find this interesting. So I want to briefly mention another lemma. Which is kind of hidden in a survey paper by Darren Long and Alan Reed. Again, an algebraic, purely algebraic factor G in a finitely geometric group. F in G subgroup, and C from F to Q a surjective homomorphism to a finite group Q. If the kernel of phi is separable, then there exists a finite index subgroup of G and a quotient map containing F H contains F.
The kernel.
No, it really contains F. And a quotient map C from H to Q such that C really extends P. Okay, so you have an arbitrary subgroup of your finitely geometric group. You have a finite quotient of that subgroup, and you're just assume that the kernel
Separable in F or separable in G?
separable in G. Okay. So a quotient of a subgroup can be lifted to a quotient of a finite index subgroup of the ambient group when the kernel is separable. And again, so I will not present a proof of this, but it's a couple of paragraphs. It's really playing. It's rather elementary. But you see, so application. So if G is non-elementary hyperbolic, you assume that G is non-elementary hyperbolic, and with all quasi-convex subgroups separable, then for every finite group there exists a finite index subgroup of G which maps onto Q. Okay, the statement is clear. So this should be compared with Hegel-Groves-Manning theory. So if you believe that all hyperbolic groups are residue finite, then all non-elementary hyperbolic groups satisfy the hypothesis here. And so they virtually map onto every finite group. So it's a lot, this formally is clearly stronger than the hypothesis of than the condition of residual finiteness. Right? This does not tell you about the algebraic nature of the finite quotients. And the proof of the corollary is just the fact that in any non-elementary hyperbolic group, you find quasi-convex free subgroups, right? Ping pong, the ping pong argument. By ping pong, G has quasi-convex free subgroups, non-abelian free. Okay, and if you pass to a further finite index subgroup, you can assume that the rank of F is greater than the rank of Q. So then F must map onto Q. And then the kernel of phi is again a finite index in F, so it's itself a quasi-convex free subgroup. So you can apply that. So, for example, one thing that you can deduce from this, it's an observation of Lubotsky. So, if some co-compact lattice in SPN1 has the congruent subgroup property, then there exists a not regularly defined hyperbolic group. So really again, so if you believe that this applies to every hyperbolic group, it means really that every hyperbolic group has absolutely any virtual finite quotients they can exist, and on the other hand, the congruent subgroup property goes strongly against this. That's a strong restriction on the nature of the finite quotients or finite index subgroups of you. Okay. So. But again, in the philosophy of my talks, so the congruent subgroup property is a kind of classification of all finite quotients of a group. And this, I think that's so proving CSP for co-compact lattices in SPN1. So these co-compact lattices are linear, so residually finite. So they do have many finite quotients. So classifying them, it's a pretty hard problem, as opposed to showing that one hyperbolic group is not residually finite. Then it's enough to find one and show that the classification of its finite quotient is kind of trivial. You see, so yeah, my feeling is that this should be much harder. Proving CSP for this kind of group should be much harder than. Of course, you need to have a candidate. That's probably that's a difficulty. A classification result when the outcome is just the trigger group should be easier than a classification result where the outcome is a counter. Okay, so yeah, I think yeah, it was good to mention this. Yeah, still related to the congruent subgroup problem, I should probably mention another example, which is SLNZ with NRT3 Okay, so this is a group for which has the congruent subgroup property, so it has few finite quotients. So then you expect that it will have few separable subgroups, and indeed that's the case in a very strong way. So if you take G to be SLNZ and H in G, any Zariski subgroup, and you can find, for example, 3 subgroups of SL and Z that are Zariski dense. Then H is separable if and only H is a finite index. Okay, so most Zariski dense subgroups are inseparable with SL and Z, and this is the way to prove this is really, the interesting implication. It relies on deep results, so you need to use CSP, the congruent subgroup property, but that's not enough. You also need to use a super strong approximation. And in this case, it's a result due to normally and vice versa. Independently. Okay, so now I want to make the connection with the lattices in products of threes, and especially with that is inside here. So I was asked to show Danny's example, so I wrote it. So again, the example which is wise, and Wise himself calls this example the main example of his thesis. So gamma is a group with 5 generators and 6 relations. So I insisted on the first lecture that you should be careful when copying the relations. You should make sure. Yeah. So if you remember my first lecture, so this gamma is a GM group of all the 3-2. So it's a co-compact lattice in the automorphism, the product of the automorphism groups of 2 trees, the 6 regular tree and the 4 regular tree. And again, Danny proved that the subgroup gamma H generated by ABC is inseparable. In fact, so he did this by hand, and so proving that this is inseparable, it suffices to find one element, not in H, not in gamma H, but whose image in every finite quotient belongs to the image. And so he did it explicitly. In fact, so X inverse Y cannot be separated from gamma H in any finite quotient. Okay, and again, corollary, the double is not really finite. So I'm repeating myself, but what's very important to notice here is that here we are doubling gamma over a specific subgroup, right? And so you can do this for any BMW group, and if you double over the subgroup generated by the horizontal generators, you get again a BMW group. So remark, and so the fact is that this is a BMW group of order 3, 4. I leave it to you as an exercise to write a BMW presentation for this.
Gamma H is always free, right?
Absolutely, yeah. So fact is gamma less gamma B a BMW group. Then gamma H, the subgroup generated by is isomorphic of the free group of rank M. And really this is very important, but it's also easy to explain why this is the case. So gamma acts by automorphism on two trees, right? So the horizontal tree is the universal cover of the bouquet of M circles corresponding to these M generators, and this is the universal cover corresponding of the N circles corresponding to the vertical generators, okay? And now, how do I think of this group in its action on the product of the two trees? So, gamma H is the stabilizer in gamma of subvertex X some X vertex of the vertical tree. And so gamma H, it fixes a vertex in the vertical tree, and it acts freely and transitively on the vertices of the horizontal tree. And that's why it must be free. So my goal for the rest of my time today, and maybe I'll have to continue this next week as well, I would like to explain you why is it possible to find inseparable subgroups in lattices in products of two trees. I want to show that this is actually the generic phenomenon, that gamma H is inseparable in gamma. And eventually we will show that actually, even before doubling, Danny Wise's main example was already non-reasonably finite. So that will come at the end. So the goal is to study inseparability of gamma h and gamma in all BMW groups. But again, I don't want to come back too quickly to BMW groups. I will do it in an abstract framework. And what is the key property of gamma h in gamma that I will use? I will use the fact that gamma h is a commensurated subgroup of gamma. Okay, so let me now spend some time again giving definitions and examples to illustrate this concept. So we go back to an abstract setting. G is a group, and A, B are subgroups of G. We say that A and B are commensurate if the intersection of A and B is of finite index in A and B. Relation N to the B. So this relation, Friedel, is an equivalent relation on the collection of all subgroups. That's an easy fact. So G acts by conjugation on its subgroups, so it also acts by conjugation on the commensuration classes of subgroups. And so even A subgroup of G, we write some GA for the stabilizer in G of the commensuration class. Okay, and then you can check this is the collection of G in G, such that A is commensurate to the conjugate. And we say that A is commensurated if it's commensurate with the whole group. And again, an exercise is that A, saying that a subgroup is commensurated, is the same as saying that when you look at the the action by left multiplication on the cosets of A and G, you restrict to the A action, this has finite orbits. So, what are examples? Example 0 would be A normally G. A normal subgroup is commensurated in that case. You know, you have even a representative that's fixed under the conjugation action. The action of n on G mod n is then as orbits of length 1. The trigger. Slightly more interesting example would be when A is finite, or A has finite index, and then again this intersection, yeah, then you get commensuration for free. And then you can combine the two to obtain like the cheapest family of commensurated subgroups. So if A is commensurate to a normal subgroup, then A is commensurate. Right, because again, so in the commensuration class of A, you find a representative that's fixed. So the class of A is but as I said, so this is kind of the degenerate source of commensuration of commensurated subgroups. So I would like to say that a commensurated subgroup A in G is essential if A, the class of A, does not contain any normal. And then it's becoming trickier to find examples, and the kind of prototype here will be groups of arithmetic origin. Commensurates S and Z. And of course, once a group commensurates a subgroup, you can look at subgroups of G containing A, and all of them will commensurate. So you can also restrict to, for example, SLN Z, where you invert some integers with the same A. This will be, again, an example of a commensurating subgroup. And so, yeah, there are two exercises. First, to check that indeed you have a commensurated subgroup, and the other exercise is to check essentiality. But the reason why you have essentiality in these examples, so this, you have to remember that PSLN Q is a simple group. And again, PSLN over this ring is a just infinite group. So even hereditarily just infinite. So there are very few normal subgroups.
Is there some relation with non-normality?
It's kind of, non-normality is kind of a completely an antipodal condition to commensurated. So a quasi-convex subgroup in a hyperbolic group is always contained as a finite index subgroup in its commensurator, because the commensurator, if you think about it, it preserves it stabilizes the boundary of the quasi-convex subgroup. So the commensurator of a quasi-convex subgroup is equal, or is contained in the stabilizer of the boundary of the quasi-convex subgroup. So in hyperbolic groups, you will not find quasi-convex commensurated subgroups unless they will all be of finite index. Okay, so that's, arithmetic rules give you naturally examples of essential commensurated subgroups. And then there is another source of commensurated subgroup, which is of geometric nature. So let G be a connected locally finite graph. And G any group of automorphisms of G. Then for every vertex of the graph, the stabilizer of that vertex is commensurated to G. So indeed, so what's the proof? If I take an element of G, I have to look at the intersection of GV with its conjugate, okay, which is the same as the intersection of GV and GV. Okay. And now, how can I bound the index of this double stabilizer in the stabilizer of that vertex? So what's the maximal number of conjugates of that inside this? It's the maximal, is the size of the orbit of that vertex under that group. Okay? So this, the size of that orbit, if you fix the vertex, you stabilize all spheres around that vertex. So this is at most the cardinality of the sphere centered at V of radius, the distance between V and G. And I assume that my graph is connected locally finite, so this means that all these spheres are. So now I can, now you start seeing, okay? You start seeing the connection with my setup of groups acting on products of trees, right? So here is now an application. So let T be binary. Look at binary. Tree and G an automorphism of T acting minimally by which I mean without proper invariant subtree. if for some vertex, the stabilizer of that vertex is separable, then G is discrete. Okay, so I cannot give you, so the proof will come. The proof is forthcoming. To explain you why this is true, I need the main result of today. So this is this is part of a node with three co-authors, Peter, Prof, Colin Reed. So it's not Alan Reed, it's another Reed, Colin. Philip Weatherall.
And it's not Robert Crocolo.
It's not Robert, it's Peter. Thank you. PH. Have to be careful. So the result says the following. Let G be a finite unity group, and H and G be the main street itself. So I can look at the profinite logger of H, which is the intersection, as I defined before, the intersection of all finite index subgroups of G containing H. And I can look at the normal core of this, so this intersection of all conjugates. So this is an overgroup of H, and I look at the intersection of all its conjugates. Okay, and the claim is that this is a finite index. Okay. So in particular, so if H is separable, so if you're in the situation where you have a commensurated and separable subgroup, then H contains the finite index subgroup N, which is normal in G. Okay, the normal core of H. So now I can remove the twiddle and I get a normal subgroup of G, which is a finite index in H. But this is obvious. Okay, so now what's the proof of the lemma? Where is the lemma? Okay, so and I see that I forgot to assume that G was finitely generated. Sorry. direction. Finitely generated group G acting minimally on the tree. So I can apply. So we apply the theorem to GV. GV is always commensurated. So if it's separable, then we know that there is this n normal in G, such that n is contained as a finite index normal subgroup of G. P. But then I get a normal subgroup of G which fixes a vertex. Okay, so I can look at the fixed point set of n in my tree. It will be non-empty because it contains V. And this is acted upon by G. But I assume that the action was minimal. So G minimal. So this must be the whole tree T. And so n is trivial. But then the trivial group is a finite index subgroup of GV. So GV is finite. And this is exactly the same as saying that G is this group. Okay, so perhaps I should stop here for today because what I'm really planning to do is to discuss a proof of this theorem. So I'll do that next time. I'll discuss further applications. So one of them, so that you already see in this lemma is, so you see a relation between a group acting on a tree to be non-discrete and the stabilizer of a vertex to be inseparable. So if you come back to Danny Wise's example, so Danny proved that gamma h, the horizontal subgroup, was inseparable in gamma. So this happens to actually be equivalent, in his case, for the projection of gamma to the vertical tree to be an indiscrete subgroup. So actually, and this I will explain next time, so for lattice in a product of two trees, the lattice is irreducible if and only if the horizontal and vertical subgroups are inseparable. So actually, what Danny proved by hand is actually irreducibility of his group.
And am I right in thinking, I think Danny also proved that if one side is separable, then the other one is as well. Isn't that, I mean, he has a, horizontally clean implies clean result, which I think is that.
Yeah. And if you read between the lines of his paper with Frederic Agrund, you will actually see that later he really completely understood why inseparability of one is equivalent to irreducibility. And yeah, the account I'm giving is kind of an algebraic approach to seeing this. And then once I'll have clarified the link between irreducibility and inseparability, we'll continue the discussion to show that also we can find criteria of non-residual finiteness without the doubling trick. Okay, so that will be for next week. And then, yeah, of course, I have to wrap up my story and explain you how you combine the just infinite property with the non-residual finiteness. And this will require further ingredients. For today, I think I'll stop here.